Waiting for mortgage rates to drop could be a costly mistake. Once rates drop, new home buyers will enter the market and prices will soar even higher. At Churchill Mortgage, you can get a free analysis and learn how to avoid the trap of waiting for interest rates to drop. Buy now and refi later at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Introducing Carvana Value Tracker, where you can track your car's value over time and learn what's driving it. It might make you excited.
Whoa, didn't know my car was valued this high.
It might make you nervous.
Uh-oh, market's flooded. My car's value just dipped 2.3%.
It might make you optimistic.
Our low mileage is paying off. Our value's up.
And it might make you realistic.
Car prices haven't gone up in a couple weeks. Maybe it's time to sell.
But it will definitely make you an expert on your car's value. Carvana Value Tracker. Visit Carvana.com to start tracking your car's value today.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us. This is the Space Nuts podcast, heard across Australia and around the world. My name's Andrew Dunkley, your host, and it's great to be with you once again. And coming up on the show today, we're going to be dedicating the entire program to audience questions. We've got questions about satellites and the Earth's shadow, the speed and age of light, the interstellar medium, the non-existent luminiferous ether, and life, as well as quantum fluctuations. We're going to cover all those topics from our audience on the program today. We also have some news, which I think you'll find very exciting. So we'll get into that. But not before I introduce the great man himself, Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. I was just thinking at the start of the show, it's amazing how you remember all the right things to do and start with introducing me, and then you didn't. And I thought, he's forgotten. No, never mind. I'm here and lively and looking forward to our chat this morning.
Now, you're still in lockdown, and I'm expecting sometime today that I will be too, because we've officially found a case of COVID-19 Delta strain in Dubbo. So it is here. And look, I'm hardly surprised. I know a bit more than people in the public know at the moment due to my journalistic connections, but I'm not able to say anything at this point in time publicly, but I'm sure the news will come out. But yes, there is a case in town, and the source is unknown, which is even worse. So I'm expecting any time now to receive lockdown orders. So join the club. That'll mean that every member of my family is now in lockdown if we get locked down today, and it looks like it's imperative, so or imminent. So here we go again, Fred.
Yeah, part of life's rich tapestry, Andrew.
Yes, indeed. Yeah, if that's what you want to call it.
Yeah.
Dear. Anyway, who would have thought at the beginning of last year we'd still be dealing with what we're dealing with now, and I don't think it's going to go away this year or into next year, and it might even go a lot longer than that. I think this Delta strain is with us forever, and that's very unfortunate. Anyway, we're here to talk about astronomy and space science and to answer questions from the audience. So without further ado, let's get our first audio question. Now, we don't know who this is from, but that's okay. The question will become self-apparent.
Hi, Professor Watson and Andrew. Thanks for such a great show and also answering my questions. Just to let you know, I have bought a Space Nuts sticker from your shop and plan to proudly put on the back of my car. My question today is about satellites, the Earth's shadow, and impacts on the night sky. I notice on heavens above by default that it only shows the satellites going over during the dawn or twilight hours. As I understand, this is due to the site showing only visible passes. From a technical sense, my understanding is that after the sun has set, the satellites are no longer able to reflect the sun's light, and thus being no longer visible. Could there be a situation where satellites are visible during the night hours? Can the satellites transit in the night sky and the Earth's shadow still be visible or impact ground-based telescopes? The reason for my question is about understanding the impacts of the satellite constellations on professional and amateur ground-based telescopes. There is much discussion around this at the moment, and a lot of articles in the popular media around the impact on our night sky. However, it's hard to tell how much of an impact there is or will be. Is the impact only during twilight and dawn hours, or could these satellites cause an impact any time of the night? On a side note, my brother recently passed away after a year-long battle with lung cancer. He was 43. He never smoked and barely drank, but was just unlucky. He got me onto your podcast, and I hope you don't mind me taking the time to note his memory. Thank you.
Thank you so much for your question, and very, very sorry to hear about your brother, and really glad that he put you onto the Space Nuts podcast and that you both got some great value and good times out of it, and probably had some wonderful discussions together as well. So sorry to hear about your brother. It's always sad news when something like that happens, especially under those kinds of circumstances, and I think we've all been there. Fred, let's talk about satellites and their visibility and their interaction with telescopes and the potential fallout from that, given that so many are being launched into space, into low Earth orbit, and some of the controversy surrounding that in recent times. Where do we start with this one?
Yeah, it's a multifaceted one, and it's one that concerns us a lot in the world of astronomy and space science at the moment because of the influx of these mega constellations, which we're on the brink of seeing. So there's a number of aspects to this question. Let me just start with one, because it's the slightly off-field one. The satellites we're principally talking about here in the question are what are called near-Earth objects, near-Earth satellites. Low Earth orbit satellites, ones that are relatively close to the Earth. I think low Earth orbit is defined as up to 2,000 kilometres, if I remember rightly. But of course, there is another family of spacecraft at 36,000 kilometres, and they are the geostationary and geosynchronous satellites, which we rely on for communications. Now, they are so far away that most of the time they are outside the Earth's shadow. They're not within the Earth's shadow. They do pass through the Earth's shadow from time to time, but most of the time, most of them are outside the Earth's shadow. And that means that technically they are visible outside twilight. Now, against that is the fact that they're at 36,000 kilometres. They're shining by reflected light from the sun. They're small objects. So generally speaking, they are very faint. And I remember an experiment we did at the UK Schmidt telescope decades ago, where we actually photographed some of them, and they were like very faint stars. They were on the limits of detectability with that telescope. That's a 1.2 meter telescope. So generally speaking, you don't see them. However, some of them have these flat panel antennas on them, and so occasionally you will get what are called specular reflections from the sun. In other words, the sun hits one of these panels at exactly the right angle to send the beam back to Earth. And once in a while, you see flashes from geostationary satellites well outside the twilight zones. In other words, any time during the night. So that's a slightly different thing from what the question's mostly about. But that is a case where you can see them, at midnight or times like that. But generally speaking, it is true that excuse me, to the naked eye, the only time we see satellites is within about an hour or so. It depends on latitude, so it's not definitive, but within an hour or so at mid-latitudes of either an hour or so of sunset or an hour or so of sunrise. It's a bit longer sometimes, up to 2 hours perhaps. Yeah. Outside those times, the satellites are dark. They're not illuminated by the sun, and they're essentially invisible. Although for professional telescopes, of course, they might occasionally blot out the light of an object, but they don't leave a trace. They don't leave a trail on the image because they are dark. So the effect is really very minor. Outside against that, once again, another aspect of this that's not necessarily obvious. As far as radio astronomers are concerned, these things are live all the time because they're broadcasting radio signals. Depends on frequency bands and things of that sort. But none of that applies in the radio spectrum. They are they're live all the time, and indeed they actually have the capability of reflecting terrestrial radio signals back to Earth. So that's one of the worries with the square kilometre array, that radio broadcasts from Perth and Geraldton might be reflected back to Earth by satellites passing overhead. That's why things like the Heavens Above site only show when these things are occurring during twilight hours, because that's when they're visible. Just one footnote is that SpaceX has been trialing what they call their visor sats, and these are basically dark screens that actually block the light from the sun from landing on the spacecraft in order to reduce their visibility. Now, the target that SpaceX has is to push the visibility of their satellites in twilight down below the naked eye threshold, so that we're not seeing a night sky with literally hundreds of satellites going past at any time. That we haven't seen any firm reports on the outcome of that, but the discussion is ongoing, and it's part of certainly SpaceX. They are keen to try and work with the astronomical community to mitigate the effects of their mega constellations, but there's a limit to how much can be done, basically. The problem is the constellations themselves. There's so many of them. So an interesting question, and I hope that explains what's going on.
Yeah, I hope so too. But I remember as a kid often going out on the back patio at my grandparents' place and just lying down just after sunset and watching for satellites. Now, there weren't that many of them back then compared to today, but we used to get really excited when we saw this little speck of light just darting across the sky. And, we'd see other things as well. But it was a pretty exciting thing as a kid, and of course now they're a dime a dozen, aren't they? They're just so many up there.
Yeah, if you're looking at the night sky after twilight, there's a good chance you'll see one, or before sunrise. Yeah, it's.
And of course, now you can track them on the internet, so you know where and when to look for things. And of course, the International Space Station. There's a website dedicated to where it is, and so you can easily pinpoint its location and go outside and take a peek, which I've done once or twice. But it's so much easier now. And back in the day, you just sort of wonder what that was. Wonder which one that was. No idea. But is it going to get worse, Fred? Is that likely?
Yep.
In a word.
Absolutely. We've got the potential for there being 100,000 satellites in low Earth orbit. That's the number of mega constellations that are being proposed. So it's going to get worse.
Yeah, reminds me of a bad sci-fi film. Okay, there we go. And thank you again for your question. Let's move on. And this one comes from North California.
Hello, Andrew and Dr. Fred Watson. Ralph in Northern California again. I posed a question recently about the speed of light, and it probably got buried in your multitude of questions. That one was, can photons ever go slower than the famous speed of light? With gravity lensing and other ways of bending light, I would think that at some point they might go a little bit slower. The second question is, how do we measure the age of light? If we say it's 2-point-something million light years from Andromeda to reach us, how do we know that? How do you guys figure that out? For that matter, how do we know it takes 9 minutes for light from our own star to reach our planet? I've always wondered about that. Anyway, great show. Always keep it up. Thank you guys, and rock on.
Thank you, Ralph. Lovely to hear from you again. How do we measure the age of light? How do we know it takes that long for it to reach us? I'm thinking it's the thumb test. You just lick your thumb and put your finger up in the air and go, it's 8.5 minutes to get from the sun to the surface of the Earth. It's probably more scientific than that, is it, Fred?
A little bit, yeah. Let me start with the first bit of Ralph's question. about whether photons can go slower. And of course, the answer is yes, they can, because as soon as light comes out of a vacuum and into another medium, whether it's air or glass or water, it slows down. And that's why we get the phenomenon of refraction. It's that slowing down of light in these media that does the slowdown. So photons can indeed go slower than light. And there are some experiments, which I confess I don't fully understand how they do it, but there are some media that light can pass through. And when you do certain things to it, you can actually stop the photons and then let them go again. And that's a pretty amazing thing to be able to do. It happens in physics labs, a number of experiments that have succeeded in doing that. But, in the normal natural world, we see light being slowed down all the time. So that the speed of light being immutable is the speed of light in a vacuum. And that's the one that sets the speed limit. Nothing can go above the speed of light in a complete vacuum. And then the second part of the question, unless you've got a comment there, Andrew, I heard you draw a breath.
Yeah, that's all I was doing, taking a breath.
Well, don't do it.
Well, I suppose the second part of his question is about the age of light and how we determine.
Yes, that's right.
Because the funny, we have discussed how light is produced and how long it takes for a photon to actually get out of its parent star, and that's, light is old before it actually leaves. Leaves the star itself, in the tune of tens of thousands of years, or is it more? It's a massive number.
It's the best estimate is 170,000 years. This is for the sun. But some scientists think it could be up to 1 million years. It's because that's a slightly different process, though, Andrew. What's happening there is, the nuclear reactions at the center of the sun are producing photons, which are actually gamma rays. They're very high energy light. And those photons are, as soon as they're emitted, they immediately run into another atomic nucleus, and they interact with that and get re-emitted, and that process continues all the way up to the surface of the sun, with slightly less energy being released every time. And so when they leave the surface of the sun to take their 8-minute, 20-second journey to Earth, that means they're visible light. So that's a different process. That's because it's a different photon that comes to us from the surface of the sun than the one that was created in the center. It's basically they interact with the atoms around them. But Ralph's question is a really good one, and it goes to the heart of how we measure distances in astronomy. And it's not by timing the age of light. That is a construct that we build after we know how far something is away. For example, the distance to the sun was first measured by measuring the parallax of actually the planet Venus. It's why 17th and 18th century astronomers went off chasing transits of the planet Venus across the sun's disk, which only happen rarely. They mounted expeditions to do that because by observing Venus crossing the sun's disk from two different places on the Earth whose separation is known, you can work out the distance to Venus just by what we call the parallax. It looks as though it's crossing the sun's disk at a slightly different place from each location. So you make those measurements, you do all that, and you calculate the distance of Venus, and then from Kepler's laws of planetary motion, you can work out what the distance is of the Earth from the sun. So that's how that works. So what you're doing is you're using geometric methods to measure the distance. And then you're saying, well, we know the speed of light. So light takes 8 minutes, 20 seconds to get from the sun to the Earth. That's how we know that light is 8 minutes, 20 seconds old. It's not a phenomenon that is measurable by the light itself. And that's how we build up our knowledge of distances, Andrew. It's similar processes. When it comes to stars, it's the parallax again, the fact that a star looks slightly different from one side of the Earth's orbit from what it does at the other side. So then you can work out its distance. Then you build up the distance scale by looking at standard stars. I used to work on a class of stars called RL-Lyrae variables, which potentially can tell you the distance to something because they've got a fixed brightness level, which you can measure by looking at the way they vary. The variable means that they vary in brightness. That gave us an early measurement back in the day of the distance to the center of our galaxy, for example. Then you look at other sorts of variable stars, something called Cepheid variables, which are rather brighter. And it was when Edwin Hubble measured those in the Andromeda galaxy that he was able to work out the colossal distance of the Andromeda galaxy, which we now know, as Ralph says, is about 2-point-something million light years. But it's because of all these intermediate steps that you can work out how long the light has been traveling. And on the largest scales, we use redshift. We use the fact that the universe is expanding, and that expansion reddens the light because the light waves are stretched, and we can calibrate that expansion by the Hubble law, or I think it's now called the Hubble-Lemaitre law because of Georges Lemaitre, who was the Belgian priest who figured all this stuff out alongside Hubble. That lets you work out the distance to these very distant objects. So in that sense, we are, that there is a property of the light that's telling you that it's aged, and that is that its wavelength has got longer. It's been reddened because of the expansion of the universe. But otherwise, other than that, we don't look at the age of light. We look at other distance measures and then work out what the age of light is. One other thing that I might throw into this is that to a photon, time doesn't exist, so they're all ageless in their own reference scale, if I can put it that way, their own reference frame. So photons are rather interesting. They don't experience time.
Do they end? I just wonder, when the light comes out of the sun and it does its 8-minute and 20-second journey and then hits the Earth, is that the end of the photon?
Yes, actually, it is and it isn't. What happens then is something similar to what happens in the center of the sun. It hits another atom and does something to it. And in fact, normally what it does is it imparts some energy, which just very slightly heats up that atom. In fact, you've only to stand outside in the sunshine to know that you're feeling radiant heat from the sun. You're feeling infrared radiation, but also the light, to a small extent, is heating you up because it's converting its energy into heat energy within your body. So it does come to an end, but it turns into something else.
Yeah, I'm just thinking, the photon pops out. And it sees Earth and goes, oh, damn it, I wanted to live longer than that.
Yeah, that's right. Some photons are, going for 30.7 billion years, nearly the age of the universe. Yeah.
Fascinating. All right, Ralph, hopefully we adequately answered your question about light and photons and the age of light. I find it all very fascinating, light and shadows. I really do. Thanks again for your question. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Thank you for joining us. And once in a while, we like to send a shout out to our patrons and thank them for putting a little bit of their money into this program so that we can keep operating. And we've got a few patrons that have signed up recently. One of the benefits of being a patron is that we name you, but we don't shame you. We thank you. And one of those is Shane. We don't have a surname for Shane, but Shane will know who Shane is. Derek Fox, Nige Gardner, and Ashley Exetel, who have all signed up to be patrons. Ashley is actually signed up to the highest level as a patron. So thank you so much for putting your support behind us and having faith in us. We certainly appreciate it. So a salute to you. And of course, if you'd like to become a patron, you can do that on our website. Just go to spacenuts.io or spacenutspodcast.com click on the supporter link and all the options are there: Patreon, PayPal, Supercast, whatever suits you. Of course, as I've always said, it's not mandatory, but there are growing benefits to becoming a patron, which we'll be able to tell you about in the not too distant future. Now, Fred, let's move on to our next question. Now, first up, apologies for the sound quality, but we'll try and tweak that in the course of post-production.
Hello, Fred, Professor Fred, and Andrew. This is Paul from Philadelphia, USA. And I was wondering, I'd seen something on WIMS, which I believe stands for Warm Hot Interstellar Medium. And I'd seen that it accounts for a big chunk of the matter we can't see. And I know it's not a dark matter question, but maybe you could shed some light on that. And also, I'd seen that it's actually extremely hot, this matter, but for some reason our infrared satellites can't pick it up. So if you could discuss that and educate us on that, I'd appreciate it. Thanks. Love the show, and it's definitely in the top 2 of all science podcasts that I listen to. Thanks a bunch.
Thank you, Paul. Thanks for the endorsement. Appreciate it. He said maybe we could shed some light on WIMS, the Warm Hot Interstellar Medium, but I think we already shed light in the last segment. So we've already done that. But yes, he's talking about something that's somewhat mysterious, the warm, was it warm? Yeah. Hot interstellar medium? Yeah.
Yes. It's technically the warm, hot intergalactic medium, because this is what is between the galaxies. And it's really an interesting story. And it's one that's got absolutely direct links with astronomers here in Australia. So, and it's a lovely acronym, isn't it? The WIM, W-H-I-M.
Oh, yeah, it is.
You astronomers, you just have these whims and then you just get on with it. Yeah. Anyway, so what is it? It's something that is predicted by cosmological models. When you look at the way matter behaves. I'm talking now about on the largest possible scales. We know that the Big Bang generated hydrogen and helium and this stuff called dark matter. And it's not dark matter we're talking about, exactly as the question said. This is real matter. What we in the trade call baryonic matter. Baryons are normal matter. It's atomic nuclei and, just normal stuff. So you're made of baryons, Andrew. You should be called Barry, really, shouldn't you? Anyway.
Yeah, well, we all should be.
Yeah, we should, yeah. Hello, Barry. So this is normal matter that's predicted to exist within the galaxies, but in the space between the galaxies. But the mystery has always been how much of it is there. And people they've looked at the theories for the way the universe was created, the origin of the universe, the Big Bang, and how it behaved after that. And they've worked out that we don't see enough of these baryons. In other words, the amount of normal matter that we see, and it's mostly hydrogen, is not enough to satisfy the kind of equations that relate to the formation of the universe. There's something missing in our understanding, and it's actually usually sometimes called the missing matter problem, but that tends to stray into territory that is occupied by dark matter, which is something completely different. So it's better calling it the missing baryon problem, not the missing Barry problem. That's a different one altogether. The missing
He emailed me yesterday.
Did he? Good. Yeah. Should be a series of books called "Where's Barry?" Shouldn't there? That would do it. Yeah. So it's called the missing baryon problem, and there was a really what you might call a pivotal paper that came out last year, which was produced by principally Australian astronomers using the Square Kilometre Array Pathfinder, ASCAP, and our facilities that we have access to in northern Chile, the ESO telescopes, European Southern Observatory. A number of my friends and colleagues were involved with that work, a really important paper which actually won an award. Actually, I beg your pardon, I'm mixing up two papers there. This one didn't win an award. It was
just wasn't good enough.
Well, it might still do, actually, because it's an important paper. There's a poignant side to it, though, because the lead author, Jean-Pierre, I think his first name was, we'll all call him JP, Marchant, he was a young bloke. He's in his 30s or 40s. He died 2 weeks after that paper was published. It was a shock to everybody. I think he had a heart attack. Really, really tragic.
Wow.
Yeah. But remarkable work and remarkable piece of astronomy. So what that process did, what this discovery did, and it was all to do, by the way, with fast radio bursts. It allowed the light from fast radio bursts, the radio signals passing through the universe, to essentially be a tracer of what's in the intergalactic space. And sure enough, they found that there was really strong evidence for this WIM, the warm, hot intergalactic medium, at a level of maybe 1 to 10 particles per cubic meter. So it is highly rarefied. But it's hot. And when you're looking at really rarefied media like that, hot has a slightly different connotation. It just means the atoms are moving very quickly, or the particles, the subatomic particles. It doesn't mean that you could, hold out your hands and feel the heat of it. The temperature is up to 10 million degrees. It's somewhere between 100,000 and 10 million degrees. But that is, for something that's so rarefied, all that's telling you is that the individual particles are very energetic. They're moving very fast. And it's the fact that this is such a rarefied medium that explains the other part of the question. Why don't we see this in infrared? It's something that's emitting heat, so why don't we see it in the infrared? It's because it is so rarefied. There's so little of it that you don't detect it by normal infrared detectors.
Well, maybe one day if they, have much better instruments down the track that we haven't been able to invent yet. But who knows?
That's true. But the technique that has been done to detect it, which is looking at the way fast radio burst signals are modified by, it's actually a process called dispersion. It's the way the short and long radio waves are separated in the same way as a prism breaks up light into its spectrum. This intergalactic medium breaks up radio waves. It slows the long wavelength radio waves down. And so you get the fast radio burst arriving slightly later than with the long wavelength radio waves than the short wavelength radio waves. And that's what tells you there's something there. And by analyzing that, you get this measurement of the WIM. It's a great story. Yeah, I'm sorry I've gone into more detail than I intended to, but there you go. It's just too good a story to miss, and a great question.
Yeah, wonderful. Thank you, Paul, and hope all is well in Philadelphia. Let's move on to our next question from Martin.
Hello, Space Nuts. Martin Berman Gorvine, science fiction writer and newly faithful listener here with a couple of completely off-the-wall questions about the, as far as we know, non-existent luminiferous ether. If it did exist, how would astronomy be different, as this would presumably affect the entire spectrum, visible light, radiation, gamma rays, radio, everything? And could it be somehow be harnessed, luminiferous ether, that is, for space flight? Love your show. I know this is completely ridiculous and a fantasy type of question, but it would make my day if you answered it on your podcast. Thanks, folks.
Lovely to hear from you, Martin. Lovely to hear from a sci-fi writer. And why not ask us a question that's completely ridiculous? I mean, that's what science fiction is all about sometimes, isn't it? Just to take someone on a wild ride. Why not do it on our program? Non-existent luminiferous ether. You better explain that first, Brett.
I think you should, you should be taking the hint from Martin and building this into your next sci-fi novel.
As soon as I
Andrew.
figure out what it is, I might.
What it is, yeah. Well, it's what used to be thought pervaded the universe. So, people in particularly the 19th century, that's when this thinking was at its peak, recognizing that sound waves have to have a medium to travel through, whether it's a piece of wood, if you hammer it at one end, you'll hear it at the other, or whether it's the atmosphere. The atmosphere is what's taking the sound from my voice to the microphone right now. And it's because there is that medium, there is the air there that's transmitting the sound. And it was a natural thing for early thinkers to wonder whether there is a medium which transmits light waves. Once the wave nature of light was recognized, which was pretty well, in the actually early years of the 18th century, it was recognized that there's probably a wave nature to light, maybe a little bit later. Newton thought it was particles, but it was later physicists who worked out that it was waves, actually predominantly at the beginning of the 19th century. And now we know it's both. It's waves and particles. So work that one out. But it's throughout the 19th century, people firmly believed that light was a wave and thought that it might need some medium to transmit it. And that's what the ether was, the luminiferous ether. So it was experiments at the end of the 19th century, the famous Michelson-Morley experiment, that told us that the ether wasn't there. So if you imagine a stationary medium that's transmitting light, the Earth is moving through that medium. If you measured the speed of light in the direction in which the Earth is moving, and then measure it in the opposite direction, they should be different, because we know the Earth's motion is 30 kilometers per second. That's been known since we knew the distance to the sun. So that suggested that there should be a difference in the velocity of light. And it was found by many, many repeated versions of the Michelson-Morley experiment that it's not. It's the same no matter what direction you're moving in, no matter what what speed its source is moving at. And that was why the ether was basically discarded as a theory. What came next is really important, because it was on that basis that the whole construct of relativity came about. It's the fact that light travels at a constant speed in a vacuum, and it doesn't need an ether, that allows you to, first of all, work out the special theory of relativity, which says that, okay, light's a constant, therefore time and space must warp, and we know that happens. And then lead on to general relativity. So it was an absolutely pivotal discovery, the constant speed of light. So turning now to Martin's question, had that not been the case, if the ether was real, it would certainly have produced a very different view of the universe. Relativity wouldn't exist, as our modern understanding of the theory of relativity wouldn't exist. And so when you think of all the things that come out of relativity, and in particular general relativity with black holes and neutron stars and gravitational lensing, all of that stuff, I think I'm right in saying would have been dismantled by the presence of an ether. We might not have had black holes. I'm not sure whether I'm making too strong a leap of deduction there, but it certainly would have scuppered special relativity, the idea of objects moving quickly through space, and it would have. This is important, actually, thinking about it. It would have removed the speed of light as the ultimate speed limit in the universe. So there you go. That's how you do it. That's how you, in science fiction, travel faster than light, because you you introduce the ether.
All right. I'll save that one up.
Save that one up. Yeah.
Interesting. All right.
Oh, very nice question. Nice question.
Wonderful. Thank you, Martin. Lovely to hear from you. And please send me a list of your titles. I'd love to look them up. I might have written a few science fiction books, but I was motivated to do that by reading them. So, I'd love to see your work. I'm sure it's far, far superior to anything I've ever done. But thank you for your question. Greatly appreciated. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and skiing was a go.
Space Nuts.
I've got some exciting news, Fred. Remember a few episodes back, young Ashley sent us some questions, about 500 of them, I think. And at the end, suggested that we should have an I'm a Space Nuts stickers, or I'm a Space Nut stickers. And a week later, I was able to announce that we would do that. Well, it's done. There are 3 designs, Ashley, 3 designs of the I'm a Space Nut sticker. There's a black background, a white background, and a starry, starry night background. And they're available right now. In fact, they're on our shop page on spacenutspodcast.com or spacenuts.io. Click on the shop link and you'll be able to find the stickers. And apparently they are going like hotcakes already. People are really loving them. So after only a few days, they've sold very, very well, which is fantastic. And we've taken it a step further, Ashley. You can also get I'm a Space Nut T-shirts, which is unisex style. Again, the 3 varieties, the black, the white, or the starry, starry night background. And the T-shirts come in a variety of colours as well. All the well-dressed Space Nuts listeners are wearing them, of course. I am currently not. I am wearing the standard issue polo shirt. There it is with the Space Nuts logo. And to my left, the Space Nuts tote bag. There it is. See that? There we go. So all of that's on the Space Nuts shop if you want to go to our website and check it out. Okay, Fred, let's run 2 questions by you from Rusty in Donnybrook in Western Australia. We hear from Rusty from time to time. He came on as a special guest once and did a whole segment with us. But he's got a couple of questions, so we'll hit you up with the first one.
G'day, Fred and Andrew. It's Rusty in Donnybrook, Western Australia. I hope everything's going well for the both of you. And I have a question for both of you regarding life. The most likely place, I think, for life to be found is in our own solar system, because it is likely that it only originated on Earth and has travelled there through meteor or meteorite bombardment, and bits and pieces containing life may have spread to other bodies in the solar system. Outside of that, I think the chances of finding life are a lot less, simply because we know life is here. But my question for you both is, what do you think we should do if we find no life ultimately in our own solar system? Should we then take it upon ourselves to spread life throughout, as far as we can, throughout the universe? Do you think that's a good idea? I think life is the most precious thing in the universe, and it's likely that it's pretty empty out there.
Okay. Thank you, Rusty. Rusty's got another question that we're going to drop in a minute, but life, interesting theory. I don't think I absolutely concur with Rusty's concept of life only being here and should we take it anywhere else. I do believe life probably exists in abundance in the universe. I think it's just a case of the formula being right to create it. I equate my theory to the fact that life will grab on anywhere on Earth that it can, and sometimes in the most hostile and insane places where you'll find life. And growing in the middle of a massive piece of concrete in a tiny little crack, you'll get something growing. I think the universe offers the same opportunity if the conditions are right, and I think life is probably at a very small level, microbial most likely, in existence in abundance across the universe. So should we be spreading ourselves around like fertilizer? No. No would be my answer. We will, but no. Fred?
Yeah, it's a really good question. And while you've been speaking, Andrew, my memory has been stirred to an article I read a little while ago, which I've found because thankfully I bookmarked it, which exactly addresses this question. The title of the article is "Do We Send the Goo?" Which is, the ability to stir new life into being all across the universe compels us to ask why life matters in the first place. So it's a really profound look at exactly the question that Rusty asks there. It's by, and I'm sure I'm pronouncing this incorrectly, Betul Kachar, who is an assistant professor at the University of Arizona and a NASA Early Career Faculty Award recipient. She's the director of the NASA Astrobiology Consortium Muse, dedicated to understanding the evolution of elements. Is interested in the origins of life, early biology, and life beyond the Earth. Now, it's actually quite a long article, which really explores exactly this question. Should we send the goo
via a space doogie?
Yeah, exactly. Let me just read the last paragraph. The last two paragraphs is probably I'm trying to get just a summary of what she actually comes up with at the end. She says, whether we are creating new forms of life in a lab on Earth or elsewhere in the universe, we are currently creating new chemical possibilities and therefore new potential forms of appreciation and value that can affect the way we live. The technological possibilities of applied prebiotic chemistry are only now beginning to be resolved. We can imagine using chemical reactions to perform computational processes much more efficiently than silicon chips. We can imagine self-organizing organic chemical systems, engineering solutions to pressing environmental problems. We can imagine hybrid systems composed of Earth life and prebiotic chemical systems greatly expanding and stabilizing human exploration of the solar system. The origins and evolution of Earth life have always been proximal to these anxieties in human culture, and the additional capability of selectively instigating new forms of life has an equal potential to alter our perceptions of self. We experimented wantonly and without much regard for consequences on Earth itself. You can say that again.
Yeah.
The real tension moving forward derives from our own uncertainty about who we are now, who we wish to become in the future, and what we might unknowingly risk becoming in the process. We need to take a more educated approach in the future, both here on Earth and anywhere else in the universe that we go or send the goo.
Yeah.
So it's a very thoughtful article. It's on the Eon Essays website. Eon is AEION. So I point Rusty to that. Look, you've got that's clearly a cautious approach to exactly this question. Elon Musk's approach is exactly the opposite.
It is.
It's totally gung-ho. Let's get out there. Let's get to Mars. Let's pollute Mars
Martian
with
babies.
humans. Yeah, all of that. That's right. Then go from there to the rest of the solar system and eventually the rest of the universe. It really, the thing that it hinges on is how important life is. And I have to say I struggle with this question. One of the things that I take an opposite view to yours, Andrew, that whilst there might be microbial life all around the universe, intelligent life might be so incredibly rare that we could be it.
I don't disagree with that. I'm suggesting that life being rife would be a microbial level life.
That's right. So that then, that it's an almost mind-boggling question. You've got this universe, this incredible construct, 13.8 billion years old. Don't really know how it came into existence, and we are the only species that can think about it, because we're a freak in a sense. We're a byproduct of a universe that normally just produces inanimate things, maybe apart from a few microbes. But we are freakish in the sense that we can understand it and perceive it. And that seems to me to place enormous responsibility on our shoulders, not necessarily to colonize the universe, but at least to preserve the understanding. It also suggests to me, and this is getting way off the track, but it suggests to me that there might be questions, there might be what you might call physics in the universe that we are simply not capable of understanding, that we don't have the capability of addressing those questions. And that almost puts you into a kind of spiritual regime. It's something different from what we've got, which I find...
A fifth or sixth or seventh dimension.
Yeah, that sort of thing. That's right.
Yeah. Although the fifth dimension we know exists because I love their music. It's just fabulous.
yeah. Quite so. And you've written about it as well.
That's true too. Yes. All right. Now, Rusty has another question. And again, apologies for the quality of the sound, but we'll try and ramp that up in post-production as well.
G'day, Fred and Andrew. It's Rusty in Donnybrook, Western Australia. I'm still really enjoying your stimulating show. Thank you so much for it. In the world of quantum fluctuations, some virtual pairs are said to get into an energy state that almost achieves reality, and some only exist for a much shorter time and don't get anywhere near reality. And I'm wondering if a strong enough magnetic field will coax the ones that almost achieve reality out of the virtual state into the real universe. And if so, what some of the implications of that would be, they would have to be charged particles and most likely fermions. So you'd have a positron and an electron, for example. And they could then be routed by magnetism into a combustion chamber, or on the other hand, this process may already exist in stars where you have very strong magnetic fields, and they once were in real space for a low energy cost could then recombine and may contribute to the output of stars. So implications there as well. What do you think, Fred? Cheers, mate. Keep up the great work, you two. Bye.
Thanks, Rusty. Well, I'm glad he threw that one at you.
Yeah, I don't know the answer to that, Andrew. I mean, we're talking about the creation of virtual pairs. I guess the place where there is some, it's not really experimental evidence, it's still only theoretical evidence, but actually seems to work quite well because it's been tested by analogues. The place where that really turns into reality as distinct from something virtual is on the event horizon of a black hole, where you get a virtual pair of particles come into existence. One side gets trapped on one side of the event horizon. One particle gets trapped on one side of the event horizon. The other particle gets trapped on the other. Yeah. And you've got Hawking radiation, which is real. Hawking radiation, theoretically at least, exists. It is, and it's electromagnetic. It's broadband electromagnetic radiation, so it's at all frequencies. So there is a situation where that the kind of thing that Rusty is talking about applies. But I have to say, I have no insights. My physics does not stretch to the level that would let me be able to say whether a strong magnetic field, would actually turn a virtual pair of particles into reality. I don't know the answer to that. My guess is no, but it's nothing more than a guess.
Yeah, well, it's probably
Rusty,
dark energy. Dark energy would do it.
Yeah, I'm not sure about that.
No, making this stuff up.
I was just going to say, Rusty, your questions are always really great and insightful, and very much probe the limits of my knowledge of physics.
Indeed. To use the Australian vernacular, Rusty, dunno.
Dunno. Yeah, that sums it up. Yeah.
All right, Rusty, thanks again. Lovely to hear from you. Hope all is well in Donnybrook. I'm going to get over there one day, but I think we've just been put into a snap lockdown, Fred. I've just got the alert up on my phone, so
probably
won't be going to Donnybrook today.
From 1 p.m.
Yeah, there you go.
There you are. Your lockdown's from 1 p.m.
That gives me 2.5 hours to get myself organised.
Get yourself organised, yeah. Go and buy your toilet rolls.
Yeah, it's probably too late. But anyway, that brings us to the end of the show. By the way, if you do have a question for Fred, you can certainly log it at our website, spacenuts.io or spacenutspodcast.com. Click on the send us your voice message link. It's on the right-hand side. Or the AMA tab, but there's a little button on the right-hand side, so you can send your audio questions or you can send them via text by clicking on the AMA tab. We'd love to hear from you, and thanks to everybody who's contributed today. Before we go, Fred, some dark humour from Judd Brown. He sent me 2 really hideous but appropriate jokes. A black hole walks into a bar and orders a drink. The bartender asks if he'd like food with that. The black hole says, "No, thanks. I'm a light eater." Dear, oh dear. And
classic.
A black hole walks into a restaurant and orders spaghetti. The waiter brings a serve of lasagna sheets. The black hole says, "This isn't what I ordered." The waiter said, "I figure you could spaghettify it yourself."
I thought that might be coming. That's a great one. Yeah, that's a really good one.
But yeah, thank you, Judd. Judd contacts us from time to time, and I know he's got a wicked sense of humour, but I like those. They're very good.
Yeah, brilliant.
Fred, as always, thank you so much. Nice to talk to you. We'll catch you again in the next episode.
Sounds great, Andrew. All the best to you too. See you soon.
Professor Fred Watson, astronomer at large, part of the team here. Thanks again to Hugh in the studio, who's doing nothing, but he tells us he does a lot, but really, I'm not so sure. And from me, Andrew Dunkley, thanks again for joining us on Space Nuts. We'll catch you in the next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.